In this series of videos I'm attempting to repair this. It's an HP9830A desktop calculator. It's a very interesting machine. It's very early use of ICs throughout, and it's essentially a TTL component level microprocessor coupled to some hardware for keyboard input, tape input, that sort of thing. If you've been watching these videos, then you'll know that this particular machine had a huge number of electronic faults. I've repaired a large number of those. I've replaced around 100 ICs, and one of the issues with this machine is that it makes extensive use of PROMs. So if we look at this schematic, this is part of the microcode control board. We can see that it uses PROMs for creating the various control line outputs. So this is essentially a control matrix for a microprocessor, where the individual control elements are produced by the contents of the ROMs. Now, of course, that means if the ROMs fail, then the entire machine isn't going to work. But it also means that in trying to repair a machine like this, if you do need to replace a ROM, then you need the code to program into the ROM, even if you can find a suitable ROM to actually use. Now, I've got plenty of ROMs I can use for this, but I needed the code. Now, for the microcode generator, it's not too difficult to find the code online. Luckily, quite a few people have put a lot of effort into this, but one of the problems I've had is consistency in the information I've been finding, where various bits or various bytes or values were different across the different sources, and of course that makes it difficult to determine which particular version to use. Now, in some of the videos I put out a request for any information that could be fed through to me and that I could make use of in trying to repair this. In particular, the ROM card is showing a lot of faults. More on that later, but I also needed the code to check against some of the failures I thought I had, especially in the ALU, which I was fairly certain had a faulty PROM. Now, I'm very grateful to the person that left a comment and directed me towards an emulator for this machine that included a set of ROM dumps for not just the main processor board, but also for the ROMs and the PROMs that are used in the CPU cards. So if we look at a card like this, for example, this is the microcode generator controller, and this normally has a set of 7 of these PROMs. Now, of course, getting hold of the original PROMs is very difficult, but there are alternatives, and what I want to show now is how I've gone about testing these and creating a set of replacements. So we'll go over to the PC, have a quick look at how I've gone about testing these and see if any faults were found. So the two boards we're looking at are this particular board, which is the microcode controller, and the other one is the ALU board, which uses just 2 of these devices. So we're going to look at the PC and I'll show you how I went about testing these. So here we are at the PC, and if you've been watching the previous videos in this series, it probably won't surprise you to learn that I've written yet another software utility. As I said, someone pointed me in the direction of a set of ROM dumps for this machine, and that is going to save me an awful lot of time, so thanks for that, Glenn, and also thanks to the creators of the emulator. It's very useful to have this information, and it's saving me a huge amount of time. There are a few things that have cropped up which I'll go into in future videos, but in the meantime, what was at the site was a set of ROM dump files. And the main ones I was interested in were the system dump files, and really they are the instructions in the ROMs, in each of the ROMs, in octal format here. They do have the leading zeros removed, but I've again written a small utility to put the zeros back to pad them all out to 6 characters, which is what I needed to be able to convert them into hex. But I also wanted to look at the PROMs that are in the ALU and the microcode cards. I knew, or I suspected, there was a fault in the binary ROM on the ALU, simply because of the way the machine was behaving. And so while I'm waiting for my ROM boards to be delivered, I wanted to go through these, and having access to these dump files makes life a lot easier. Before I look at those, just a quick word on the main system ROM files. These are a file per ROM in effect. Now, the way the machine's configured, if you've ever programmed microcontrollers such as the microchip PICs, then you'll know that the early ones especially used the system of bank switching to access their memory space, and that was really to keep the instruction size down, because if you wanted to address the entire memory space that you wanted to have access to, then you'd need to include as many address bits as were required for doing that. So to get around that issue and make the instruction a bit more efficient, what they did is they had a series of banks that the memory was split into. That's program memory and the RAM. And what you had to do is, especially in assembly code, is you had to select the appropriate ROM or RAM bank before you try to use it, otherwise you'd be talking to the wrong part of the memory space. And for similar reasons, on the 9830, what they did is in the first 1024 byte space, that's in the first 1K space, which is what the machine can address by default. That's in other words, if you want to go above that space, you have to start bank switching. Because they wanted to have RAM and ROM available in that 1K without having to switch banks, it'd be very inefficient to have to switch banks between reading a ROM, for example, and writing to RAM. It'd be a constant switching between the two. So they wanted to have a small area of RAM that was directly accessible within that 1K space. So what they did is they effectively mapped the top 256 words of that first 1K out of that 1K space, and they mapped 256 words of RAM into that top 256 byte space. And I'm assuming that the developer of the emulator has, because he doesn't have an actual hardware decoder, then he's simplified the job for himself by splitting the first ROM into two. That's what I'm assuming he's done here. The first ROM dump is missing the top 256 words of instructions, but they appear to be in the last ROM. So in other words, I think what he's done is taken this block of 256 words and split it out of the first ROM. Now in the actual machine, all this is in one ROM, because it doesn't matter to the machine if it's all in one ROM, because the decoding is done in hardware. So that's just a thing to bear in mind if you are going to go through and do this. Okay, so that's for a future video. For this video, what I wanted to do was to be able to test the actual ALU and microcode ROMs. Now they're slightly different. If we look at the ALUs, there are two ROMs on that card. Each is a 4-bit ROM, so all these PROMs are 4-bit. And this is the code that goes into the ALU ROM. This is the binary part of the ALU. And there's another one that's for the BCD part of the ALU. And I also wanted to be able to check and reproduce the code for the microcode PROMs. Now, if you recall, this creates a set of 28 bits that are used by the microcode controller, but each block of 4 bits is provided by a separate PROM. So in other words, the first 4 bits in all these words is the first PROM. The second group of 4 bits in all these words is the next PROM, etc. So what I wanted to be able to do is strip out each, if you like, column of 4 bits and create a binary file from those. I could do it manually, of course, but I'm lazy, so I didn't want to do that. And that's really what this software is designed to do. So if we open the microcode ROM dump, and then I select which ROM image I want to create. So if I want to create, say, the 5th or ROM 5, then I process the file. I've told it I want the ROM data for ROM 5, which in this file is actually the 3rd column of digits. And then what I end up with is a binary file that I can then open directly in my programmer. And so the way I tested this is in the programmer itself. What I would do, currently I have ROM 9 plugged into the programmer. You can't see it, but it's just off to one side here, and I've got PROM 9 plugged in. So I've got the microcode ROM dump. If I select ROM 9, process the file, I've now created and extracted the column of digits required for ROM 9, converted it into hex and written that to a file. So if I now load that file into my programmer, we can now see this is the binary data required for that particular PROM. As I say, I've got the PROM plugged in, the original PROM plugged into my programmer. So what I can do now is just verify, because the code that I've got in the buffer for the programmer is taken from the ROM dump, and if the PROM is working, assuming the code's correct of course, then verify should work, and the two should be the same. That is, the contents of this PROM and what's in the buffer should be the same. And as you can see, we have success. Now I've tested this with all the PROMs on the microcode generator, and now we'll have a quick look at the 2 PROMs for the ALU and see if they're okay as well. Okay, so I've plugged the BCD PROM from the ALU card into the programmer, and we'll use the software now to extract the data for that particular ROM. Process the file. I need to make sure we have the first block selected, because obviously these blocks don't exist in this file. Process the file, and what I can now do is open the same file, and this is now the information that should be in the BCD ROM, and I've got the BCD ROM plugged in, so I can just verify, and as you can see, that's fine. I'll do the same thing now with the binary PROM. So the ALU has 2 PROMs, one for BCD calculations and one for serial or binary. Now the machine will actually run with a faulty BCD ROM. It'll just give weird mathematical results, but essentially it won't run properly at all if this particular ROM is not working, simply because it's used for so many things. So we'll do the same thing. We'll load that file. This is the information that's in that particular ROM, and then we'll verify it. And as you can see, it's come up with a failure. It's come up with quite a few failures, and looking at the data, it looks like bits 0 and 1 are not actually working. So I'll just make sure it's properly seated into the programmer. Sometimes the pins don't make proper contact. I have done this quite a number of times, by the way, so I'm fairly confident that it is a faulty PROM, but I'll just run it again. As you can see, we get exactly the same results every time. So this particular PROM is, of course, faulty. What I did then is exactly the same process, and each of the ROMs I took an image from the ROMs, except for this one, of course. I saved those to a binary file, and so I now have a full set of binary files for these PROMs, and I programmed a completely new set of PROMs. So we'll go back over to the machine. So what I end up with is a complete set of replacement PROMs, including a replacement for the one that we know is faulty, and also, of course, a set of nice fresh PROMs for the other devices, which I can then keep as spares. I'll just get these out of the way. Okay, now one of the things I really don't like about this machine is the cards are very slightly too close together. What I normally do when replacing ICs on old equipment or even new equipment is I fit sockets rather than soldering the devices directly to the boards. This makes it easier if the device was killed by something and needs replacing again, or if it needs more work in the future. It just makes the whole thing a lot more straightforward. The problem with this machine is the boards are so close together that if you fit ICs into sockets, as you can see with this device, then they actually touch the adjacent board, or at least they're very close to it, and if the pins are slightly too long on the board that it's next to, it could end up shorting out if you're not very careful. So it was a bit of a dilemma whether I was going to solder the new PROMs directly into the board or fit IC sockets to mount them into. And I've decided that although it makes the board slightly more difficult to fit, I am going to use sockets for the PROMs. I won't use sockets for the other devices, but for the PROMs it does seem to make more sense. So what I'll do now is get the sockets fitted, get the boards put back into the machine, and see if we can progress any further through the code. And thanks again, Glenn, for pointing me in the right direction for the hex files.